All right, this is Mr. Mays coming to you not live but via video. Pleasure to have you around. Super excited to talk with you today. We're going to be messing around for the most part in today's video lesson with z-scores, and kind of the equation related to z-scores is that z-scores are equal to x, your data point, whatever data point that might be, minus the mean that you have for your normal distribution divided by the standard deviation. Now, the reason this is so exciting is we've been talking for the most part with our quantitative data about mostly median, and we've been pretty vague about center. So for the first time now, we're really digging into what it is to have a mean. And so the first thing I want to do really quickly is just show you sort of the nomenclature, the letters we put in place. The equation should look like z equals x minus this weird looking mu, which stands for mean, over standard deviation. You know, I like to call it like the little blueberry down there, okay? And all of this is to make sense of a normal curve or a normal distribution. That should look like a beautiful bell shape, okay? And the important things to recognize about this normal distribution, of course, are that the mean is in the center with the mode, and that a standard deviation is to the left and to the right of that. One standard deviation to the left, I'll make it negative to show that it's to the left, and then one standard deviation to the right. Okay, positive because, of course, in this case, we're moving toward higher values versus lower values. Okay, and we know that it's a symmetrical distribution as well, which is why z-scores are so helpful. Z-scores help us find percentiles. They are a specific version of your normal standard deviation. You can see we're dividing the standard deviation into the difference between a data point and the mean itself. So if we're thinking logically, what we're doing here is we're saying, well, okay, look, there is some amount of distance between any given data point and the actual mean, right? Let's say the mean for a test was like 86, right? And let's say you, because you're an absolute unit or a legend, score a 92. Well, the first thing I'm doing is I'm finding the difference between those two values. And of course, if your value is lower than the value of the mean, it'll be a negative number, which is, you know, should make sense, right? Because it's pulling us to the left of the mean. But in this case, you did better. So you'll have a positive number on the top. So the first thing we do is we find that difference. So in this case, that difference would be 6, right? And that's our numerator. So it would be, already we have your z-score would equal 6 over whatever our standard deviation is for this particular quiz. So that means how many points do you have to go to the left and the right to gather a certain amount of data? You may remember we first talked about if you go one standard deviation to the left and to the right, altogether, that holds 68% of the data. Now, remember, that's a little different than percentile, because percentile will be, you know, hey, you're at this percentile, so this is how much data is all the way going back before that, okay? So all of that curve underneath. Versus the thing I'm talking about specifically is just that in this center spot, within one standard deviation to the left and to the right, we'll have 68% of the data. And we'll go into more detail on this in the next set of video notes and in next class period. But what I want you to get out of this so far is, and now we're back down here, that the standard deviation is important because it tells you how far you have to travel from the mean to get a certain amount of results. So let's say our standard deviation was 3. Which means if you were to go 3 points lower than the mean, so from 86 to 83, or 3 points higher than the mean, from 86 to 89, that will hold 68% of the scores that we got in the class, okay? And so that would mean that your z-score would be equal to 2. You'd have a z-score of 2.0. Now, the wonderful thing here is because your z-score is a whole number, you already know that that means it's 2 standard deviations. I'm gonna put a plus here because it's 2 standard deviations to the right of the mean. Okay. Now, really quickly, I just want to let you know, let's say you want to know what that looks like as a percentile, okay? Well, the wonderful thing is you can do this both with, you know, whole numbers like 2, and actually I'm realizing here this standard deviation I made looks kind of like a 0. Let me make it, oh, no, I made it more hideous. It's all right, let's forgive Mr. Mays for a moment. And now he'll make it cute again. Standard deviation, something like that. Okay, so we know that it's 2. And I shouldn't have put 2. Well, 2.0 is fine, but just to clarify, it is the number 2, right? I did 2.0 to show that, right, we could put decimals there if we got a decimal answer because it is a z-score. So let's say for the sake of argument, we're over here now, that we have a z-score of 2, right? Also known as like a standardized score, right? So we have that z-score of 2. What if I want to know that as a percentile? Luckily, all of AB Stats is calculator. We love that, right? So you're going to have your TI, which you finally have access to. Thank you, the universe. Okay? And here's what we do. I'm actually going to do it on the calculator as I give you the steps, but here are the steps really quickly. 1, you go second, which is the blue button in the top left, and you click the button that says vars. And if you'll notice, the blue writing above vars says distribution. That's what it is that you're hitting, is the distribution button. So if you do second vars, you'll see the first thing under distribution, top left, is normal PDF, and then normal CDF is the second one. So the second thing you want to do is you want to pick normal CDF. And we'll talk about what all these mean soon. Once you click enter on normal CDF, you should see lower, upper, the sign for mean, and then the sign for standard deviation, and then paste. So you'll see lower, upper, mean, and standard deviation. You want to set your lower to -99. It may be -1e to the 99. It might be a bunch of things. Just delete it and put -99 in for your lower. What you're saying here is go as far back to the left of my distribution as you can. Make that my lower bound. For your upper, you're going to put your z-score in. So this should make sense for people who've done calc before. What we're basically saying is, give me all the values between the lowest you can think of and my z-score. So if I'm thinking of my normal curve, let's say my z-score, for you it's a 2.0 we agreed, so it's going to be way out here. It's going to be doing really well. But you're saying, hey, go all the way back to -99 where there are no values for a bunch, and just add up all the values between these two, okay? And then you will keep these the same, the standard deviation and the mean, right? The mean will be 0, standard deviation will be 1. And then all you have to do is go down. So I'm going to do yours 2. Go down and click paste. So let me write that. Go down to paste and click paste. And then click enter. And you will get a decimal. And multiply that decimal by 100. So I got 0.977 about. And then we do times 100, and that gives us 97.7. And that means you are in the 97.7 percentile, which makes a lot of sense because you are 2 full standard deviations above the mean. Okay, so the first thing you should feel comfortable with here is this equation in every conceivable sense of this equation. You should understand what x is, what the mean is, what the standard deviation is, and what a z-score is. You should also understand how to interpret a z-score, how to understand what that would look like vaguely on a normal distribution graph, but then also how to use your calculator to find the exact percentile that represents. Okay, now with that, you're gonna get a lot of word problems where they give you values, and you're gonna have to know, and I just wanna be very clear about this, if they give you, oh, blah, 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 Judy has a, well, I think Judy is one of the questions on one of my homeworks. So actually, let's pick another name. Let's say Jafar, the villain from Aladdin. Great character, right? Let's say Jafar has a value of 70 on some test, okay? We should already know when it says like Jafar has a value of 70, that that's X, okay? So X is gonna be like a single value, normally of an individual that they're talking about in the question, okay? That's what X will be. Don't worry about this 70, I'm just picking a random number. But like that's what X will be, is like a single value in relevance to the question. If they say standardized score or has a z-score of, you'll know that that's, oh goodness me, the z-score, right? Z-score, aka standardized score, right? And we'll understand those. Z-scores are pretty easy to understand because they will look like specific standard deviation measures. And actually, I should use my beautiful standard deviation notation. And remember, standard deviations will have a number associated with them. Like we'll say it's 1 standard deviation away from the mean or 2 standard deviations away from the mean. And those metrics are similar to what a z-score is doing. But a standard deviation has a value. Like I said earlier, that the value for your quiz standard deviation was 3. That means you have to move 3 points for it to be 1 standard deviation. So that's a metric, okay? That's what will be on the bottom, will be the standard deviation. They'll say like the standard deviation is blah. And you'll know that's how far you have to move to the left or the right to get a certain number of results. And then the mean, of course, will be the average. So if they say the average for the country is blah, or the mean is blah, they'll tell you that. And what you'll have to do is you'll have to be able to take your z-score equals x minus mean over standard deviation equation. And sometimes, right, you'll get the z-score, oh goodness me, let's make it the highlighter. I like the highlighter better for that, it's cuter. Sometimes you'll get the z-score, the data point, and the mean, but you'll need to find the standard deviation. Or sometimes you'll get, right, and it all varies, right? But it basically is to say you could get any of the 3 of these 4 values and find the 4th one. You'll need to be able to algebraically work that out and then use your calculator to solve it. Okay, so hopefully we're feeling pretty confident about this equation, what it means and how we use it. We just went over an example of what might happen, but an example to keep in mind would be something like if I said, you know, a good example would be like comparing different values is another thing that we sometimes do. So like, and we saw this in the notes in class, but like if we see that somebody is a certain height, so I think one we did was like so-and-so is a certain height, so-and-so is a different, is going a certain speed, how do we compare these values? So I think the example we had from class was so-and-so is 178 centimeters tall, and already I know that's my x data point. The average height, I saw average, so I go, that's a mean, is 165. I'll just say 65 flat. And we see a standard deviation, they tell us, of 6.5 centimeters. These are all in centimeters. And all right, I could already get a z-score from this, okay? And that's what I would have to do. I would gather this z-score. And then I would find another metric, which in this case was running. And I say so-and-so runs a 650 mile. And the average for that person for their age range is a 904. And the standard deviation is 38 seconds. Now for this one, you'll remember from class, we have to make sure that when we find the difference between the x value and the mean, we convert that final answer to seconds entirely, because then it'll work well with our standard deviation. And then we would take the z-score that we get from all of this, and we'd compare it between these 2 z-scores. And what we found in class was, in fact, the z-score for the person who is fast was higher than the z-score for the person who was tall, which was lower. And because this one was higher, that would mean that the runner, right, was faster than the tall person was tall. Okay, and that's what that means. We're basically taking 2 totally different metrics, but because we're talking about z-scores, we're able to compare them on a normal curve and say which one would be better. And if we wanted to then find the percentile, we would take that z-score and plug it in with norm CDF norm CDF, and we would be rocking and rolling, or normal CDF, I guess is what it technically says. Okay, we're rocking and rolling. We know how to use these equations. We understand the different ways they might present, and we know how to find a percentile with them. The questions will be a bit finicky moving forward because I want you to understand the difficulty of these things, but that'll be in future notes. The last thing I want you to understand is transforming data. And the 2 main ways we do it are we either add or subtract, or we divide and multiply data points. And I'm talking about when we do that across the board. And we saw some examples of these in class, but let's talk about add and subtract for a second. Let's say I have a data set, 1, 2, 3, 4, 5. These are all the values, okay? And let's say I give you a reason in a question. Now, it's not going to say add 1 to every data point, but let's say it says like, hey, you know, it turns off all the measurements were off by a pound. So what are the real measurements? So you would do +1 to every data point. So the new data set, when we make that adjustment, now becomes 2, 3, 4, 5, and 6. Okay. And what you'll notice is that a few things have occurred here, right? All of the values have moved up, right? So the things that are going to change are measures of center. And you should already know what that means because we've done measures of center. We did that to do CSOCs, but that of course means mean and median. And I'll just show you median for the sake of argument. You can see that the median for the new data set is 4, but the median for the original was 3. So whatever change you do, you will make that change to the measure of center. For all intents and purposes, that is the only change. So what does not change? Will be shape. Shape will not change. It'll still be the same shape, but stretched over a different region. And the range, right? So spread will not change. Why? Well, because my first and my last data point all changed the same way. So 6 minus 2 is still 4, the same way that 5 minus 1 is still 4. So that means IQR doesn't change. That means standard deviation doesn't change, aka this thing, right? That little blueberry doesn't change. And that means range doesn't change. Okay, so that's for adding and subtracting. And the same goes for subtracting. On the other hand, with multiplying and dividing, we get a little more change to our biscuit, as it were. What changes, and again, we'll do 1, 2, 3, 4, 5. And let's say for some reason I do times 2 to that. So times 2, it becomes 2, 4, 6, 8, 10. The things that change, of course, measures of center, and they change in the same way as you would expect. They go up times 2. So the mean and the median both go up by times 2. The other thing that changes is spread changes this time. So both measure of center and spread, so range, IQR, these all will change when we multiply or when we divide. The things that do not change, and it's just one thing, is shape. And you'll just need to know that in terms of if you have a question where it says like, will the shape change? No, it won't. Okay, that's all I'm going to say about that for now, but that should make good sense. When you add or subtract, the things that will change are your measures of center. Your measures of spread, like standard deviation, range, interquartile range, none of these will change. On the other hand, if you divide or multiply, you will find that both the measures of center and the measures of spread do change the same way. So in this case, it was times 2, so times 2. But it would be divided by or multiplied by a different value if it were a different change we were doing. And the only thing that doesn't change across both of these is shape. All right. I hope you feel like you have a pretty solid grasp on the way we can transform data distributions, the ways in which we can mess with this equation for Z-score to solve for different values, whether it's the data point, the Z-score itself, the mean, or the standard deviation for that value, how you can compare those kinds of values like we did with the speed versus height, and then of course, how we can understand percentile using norm CDF. You have been a legend. Thank you for bearing with me. You are a hero. I wish you were here with me so we could high five, but I'm proud of you. This has been Mr. Mays signing off.